All right, so let's look at another example here. So I've got a differential equation, d squared dy by dt squared plus 4 dy dt plus 3y equals this cosine function. All right, so we've talked about sort of our three basic steps, right? Step one is basically to get the transient response. Step two is to get the particular, and then step three is to put them together to get the total solution. So let's try to go through this process here. So step one is to try to get the transient response. So to get the transient response, we have to get the characteristic equation, right? We've been pretty clear about that. To do that, I first get the homogeneous equation, which is to say that I substitute in, I'm looking for, in this case, y sub c, we call it. So d squared y sub c by dt squared plus 4 dyc by dt plus 3yc equals 0, right? That's our homogeneous equation. We get rid of the driving function here on this side of the equation and replace it with 0, right? This allows us to figure out the part of the response that's coming just from the system itself and not from the input. So we said our approach to this is always that we guess a solution, and the solution we guess is y sub c equals c e to the st with c not equal to 0. So I plug that in here everywhere, right? C e to the st by dt squared plus 4 times the derivative of c e to the st plus 3 times c e to the st. And then we take the derivative, right? We take the derivative, and if I take the second derivative of e to the st, I get an s squared. So what this works out to be is that I get s squared plus 4s plus 3, and then I get a common factor of c e to the st, okay? And because we said that c is never equal to 0, right? We didn't allow that. And we know that e to the st is never equal to 0 either. It must be the case that of these three products here, s squared plus 4s plus 3 must be the term that is equal to 0. So now I have to solve for s, okay? Now, to solve for s, in this case, it's pretty straightforward. What I said I usually do is I usually go into Matlab and I say roots, and then I have a row vector where I put in the second order coefficient, which is 1, the first order coefficient, which is 4, and the 0 order coefficient, which is 3. And this will tell me what they are. Now, in this case, this is a really simple one, right? I know how to do this one from just basic algebra in high school. I'd say this is s plus 3 times s plus 1. If you FOIL those out, you're going to get s squared plus 4s plus 3. So that tells me in this case, I have s equal to -3 and s equal to -1. As I've said all along, that better be the case. What I have from this, right, in this particular case is I have real parts of my solution that are both negative, right? Real parts of my solution better always be negative. When I look at this, when I have two real roots, and those real roots are distinct, we said that's an overdamped solution, right? So we said we had 4 possibilities. The overdamped solution is one where S1 and S2 are both real and are distinct. And so that gives me a solution like the one that's shown here, right? A solution like this. Now we said this is always the solution. In general, our solution is always going to be 2 exponentials. It's just those exponentials may be complex. So if I look at this, I have C1 e to the S1t plus C2 e to the S2t. All right, and those are going to be 2 decaying real exponentials. So later on, we're going to solve for C1 and C2. We're not quite there yet, though. All right, our next step is to find the particular solution, which in this case, our input to the system was 4 cosine 10t plus 45 degrees. Now there was a u of t multiplying it, which means that this is true for t greater than or equal to 0. All right, so the way I think of it is this differential equation that I wrote here, right? This differential equation came from a real system, okay? That real system could be a circuit, all right? If that's the case, then this would be something like a voltage source, right? This input here would be a voltage source that would be driving that circuit. Now, to keep things simple, I kept this as just a pure RC circuit. So this wouldn't give you a second order differential equation, but the same basic principle is the same. And I wanted to take a look at this particular example right here. So if I have a cosine omega t plus phi x as the source, the way we talked about trying to deal with this is we said, well, this cosine is the same exact thing as the real part of a e to the j phi x e cosine omega t. And you should be able to see that, right? If I wrote out for myself a times e to the j phi x e to the j omega t, this would be a cosine omega t plus phi x plus j times a sine omega t plus phi x. So what we do is we said, all right, I can try to analyze the differential equation, solve the differential equation. If I just pull out this term right here, which we call the dynamic phasor, if I just put that dynamic phasor into the system, deal with this thing as if it's a complex input, and then at the end, take the real part. So that gave us this process for sinusoidal inputs, where I said, I guess a solution that's b cosine omega t plus phi, right? So I know that that's the real part of this dynamic phasor. So what I do is I convert this non-homogeneous equation into the complex exponential domain. So I basically try to jump over to this system and say, we're going to just use dynamic phasors to solve everything. So over here, we're using dynamic phasors. So I get that sinusoidal input into its dynamic phasor. Then I substitute this dynamic phasor for the solution into that non-homogeneous equation. That gives me two equations, one for the magnitude and one for the angle. And then I take the real part of that dynamic phasor at the end, okay? So let's go through that process. So in this case, if I look back to my differential equation, right? My differential equation was essentially this. I had dy p by dt squared plus 4 dyp by dt plus 3yp equals 4 cosine 10t plus 45 degrees, like so, okay? And this is for t greater than or equal to 0. So if I look at my steps here in this particular case, right? So I guess a solution, since I have an input of this form, cosine omega t plus 45 degrees, I'm going to say that I'm going to guess a solution of this form, okay? So I actually just want to change this a little bit. I'm going to call this omega, and I'm going to say omega equals 10. I like to keep things in variable form. So if I follow through my steps here, I'm going to guess my yp. So step one in this process, all right, step one was to guess the solution. So in this case, my yp, I'm going to say is b cosine omega t, where omega is 10, plus phi. The things I don't know here are b and phi, right? These are unknowns, okay? And I said this guy is the same thing as the real part of b e to the j phi e to the j omega t. You need to get really comfortable with that relationship. Now, step two is to get the non-homogeneous equation into the complex domain, which means to take this guy here and put it all in terms of that dynamic phasor, right? So step two here for me is to say I have d squared yp by dt squared plus 4 dyp by dt plus 3yp equals 4 e to the j 45 degrees times e to the j omega t. Now remember, this guy here was what we call the static phasor. That's the thing you're using all the time in 2112. So I've got my equation in that form. Now I got to keep going, and I want to in step 3 substitute b e to the j phi e to the j omega t. So substitute in my yp guess into that equation. So now I go into step 3. So step 3, I say I have d squared by dt squared of b e to the j phi e to the j omega t plus 4d by dt of b e to the j phi e to the j omega t plus 3 times b e to the j phi, or is it 3? Yeah, 3. b e to the j phi e to the j omega t, all equal to, right, 4 e to the j 45 degrees times e to the j omega t. Now at this point, what do I have to do? I'm basically now kind of on to the step 4 piece here, right? What I have to do is I have to write out 2 equations that are going to come from this. Before I can do that, so my 2 equations, one of them is going to be for b, one of them is going to be for phi. Before I do that, I got to take the derivatives here. So if I have e to the at, okay, if I take its, whatever nth derivative, right, what I'm going to get from that is a to the n e to the at if I go through that process, right? So in this case, a, right, if I look at what I have, e to the j omega t, so a is j omega. So what I'm going to get is that j omega is going to come down whatever number of times the derivative is. So if I have the second derivative of e to the j omega t, I'm going to get j omega squared come down. All right. This guy's going to be times b e to the j phi e to the j omega t. That's the second derivative of that, plus 4 times, okay, so in this case, I've got a first derivative, right? So first derivative means the j omega comes down. So I get j omega times b e to the j phi e to the j omega t plus this term here, there's no derivative, so I just have 3 e to the j, or 3 times b e to the j phi e to the j omega t. All this is equal to 4 e to the j 45 degrees times e to the j omega t. And remember, although I haven't written it here, omega is a number. Omega is given to us, it's 10. All right, so when I look at this, the first thing I see is that each of these terms on the left has an e to the j omega t, as does the one on the right. So that means e to the j omega t can be factored out and canceled. So this whole thing becomes here j omega squared plus 4 times j omega plus 3 all times b e to the j phi, which is equal to 4 e to the j 45 degrees, right? I did some basic algebra there, right? I said I've got b e to the j phi in each one of those terms. So I factored them out. And then I have j omega squared, 4j omega, and 3 here by themselves. Now that, I said, is effectively 2 equations. Now the thing that I want to remember here is omega is a number. I said that omega is 10, so I know what that is. If I have j omega squared, right, j omega squared would be j 10 squared. If I take j times j, right, j times j is square root of -1 times square root of -1. That equals -1. So that turns this into -10 squared, or -100. Okay, so what does this become? This guy here becomes -10 squared plus 4 times 10, so plus 40j plus 3 times b e to the j phi equal to 4 e to the j 45 degrees, like that. So there's our equation, right? And I said that's actually two equations, right? So when I look at this, this is two equations, one for the magnitude and one for the angle, okay? One for the magnitude and one for the angle. I'm going to write it like this, though. So I'm going to say for the moment, what this looks like to me is b e to the j phi equals 4 e to the j 45 degrees divided by 3 minus 100, right? So 3 minus 10 squared plus 40j, like that. That to me is actually two equations. If I take the magnitude of both sides, right, what I'm going to have is that if I take the magnitude, right, I'm going to have b equals 4 divided by the magnitude at the bottom. So 3 minus 100 plus 40j, right, like that. That's one equation. The other one I'm going to get is that phi, so if I do the angle, right, the angle phi equals 45 degrees, which is the angle at the top, minus the angle of 3 minus 100 plus 40j, whatever that is, okay, which we could easily calculate. So that is my two equations. Now, remember this form though, because I can handle this in Matlab pretty easily. So here's what I did when I put this into Matlab. So I said before, one of the things I always do to solve for the values of s, to solve for the roots, is to use this roots equation. Now remember, we had s squared plus 4s plus 3 equal to 0. So here's how I created the coefficients in a vector. And then what I did was I said, well, on the previous slide, when I was solving for b and phi, I had b e to the j phi equals 4 e to the j 45 degrees divided by 4j, or sorry, well, let me do it. So I'm going to do it this way, 4j omega. So 4 times j omega plus 3 minus omega squared, right? Where I had simplified it because I said omega was equal to 10. That was the equation I had. Now, notice what I did. I wrote omega equal to 10 as a variable, and then I put this equation in right here as an expression in terms of those guys. There's that expression, right? Now, notice a couple of things. 4 e to the j 45 degrees. MATLAB assumes the exponential function is in radians, right? So I had to convert the 45 degrees into radians. That's why I multiplied by pi over 180. What I did was I called this B complex, right? So in the terminology that I'm using here is I called B e to the j 45, I called that B underscore complex. So that is a number that is a complex number with a magnitude and an angle. So I solved for B complex, and then I said, well, if I took the magnitude of B complex, the magnitude of it would be B, and the angle of it would be phi, okay? And I multiplied here by 180 over pi to see that angle in degrees. And I see that B is 0.0381 and phi is negative 112.5902. So what I have is 0.0381 e to the j negative 112.5902 degrees e to the j 10t. This now is my particular solution, or at least the dynamic phasor for it. The very last step we had, the step 5, was to take the real part now to figure out what is the actual input, right? So what I say is that YP, the actual YP, is the real part of this expression, which is going to be 0.0381 cosine 10t minus 112.5902 degrees. Now, I am not going to lug everything around that way. I almost never do. I like putting things in terms of variables, right? I like to say this is b cosine omega t plus phi. That way I can't transpose numbers and make tiny mistakes as I move on from here. Now, at this point, I'm done my second step. Okay, I've got my particular solution. What I have to do is put everything together to find the total solution. So I have to take yp and yc and put those together, right? This guy has a couple of steps. The first step is to just put everything together to get the solution. All right, that's what I did here. We said our transient response was of this form, C1 e to the S1t plus C2 e to the S2t. And then we just solved for b and phi in my particulars. That's my total solution now. What I also have to do is take the derivative of that thing, okay? So if I take the derivative of that, what I end up getting is, all right, in this case, minus omega b, right? Omega was 10, so I'm calling it omega again. So minus omega b sine omega t plus phi. Plus I have to take the derivative of these guys. So this derivative is going to become S1 C1 e to the S1t plus S2 C2 e to the S2t, all for t greater than or equal to 0, right? So there now is, so I need these two things, because remember, I need to solve for in this step C1 and C2. I know everything else, even though this looks like it's in terms of variables, right? I know everything here except C1 and C2. So what I do after this, right, is I basically say to myself, all right, I need to use the values of y0 and y prime of 0 that I was given, my initial conditions. So the way that I look at this normally is I say, well, I know that this guy is yp plus c1 e to the s1t plus c2 e to the s2t, right? I can look at this a couple of ways. I can look at this in this general form. If I took the derivative of this expression, just as it's written right here, the derivative of this thing would be y prime of t equals yp prime of t. So that's the derivative, plus the derivative of these exponentials, which just brings down the exponent. Okay. Like that. Way I look at this is I say, all right, if I plugged in t equal to 0, right? So if I looked at y of 0, right? In this case, I was given these two conditions. Y of 0 is 0 and y prime of 0 is -1. Forget that I have values for those. If I just plugged in y of 0, I would get that this is equal to whatever yp of 0 is, plus, right, e to the 0 is always 1. So this becomes c1 plus c2. And for the derivative, it's equal to whatever the initial value of the derivative of the particular solution is at 0, plus S1 C1 plus S2 C2, right? I just plugged in t equal to 0 into these two relationships. If I look at that, right, I can turn that into a system of equations pretty easily in a very general form, right? The two things that, so a system of equations, meaning I have two unknowns and two equations. And the two unknowns in this case are C1 and C2. So the way I look at this is I say y of 0 minus yp of 0, that's the top equation, equals C1 plus C2, right? I just took this equation and rewrote it, right? I brought the yp over to the y0. And then I have y prime of 0 minus yp prime of 0 equals S1 C1 plus S2 C2. So when I look at that, right, I can create a nice system of equations from that that has this form right here, okay? So my two variables I'm solving for are C1 and C2. And the matrix here in front of it is 1, 1, S1, S2. So we've talked about how to do that. If you don't remember how to do that, you should go back through some of the earlier videos, right? It's 1 times C1 plus 1 times C2 equals this term, right? So this entry right here would be y of 0 minus yp of 0. And these guys here, this would be the bottom equation, right? S1 times C1 plus S2 times C2 equals this. So this would be y prime of 0 minus yp prime of 0, like so, okay? And I put this into Matlab in the form AX or AC, I think is how I have it. AC equals B, right? So B is this vector here, A is this matrix here, and C is the thing I'm solving for. So in Matlab, I would say C equals inverse of A times B, like so. All right. So with all of that, how would I put this into Matlab? All right, so let's remind ourselves here. The way I set this up is I said I had 1, 1, S1, S2 times C1, C2 equals y of 0 minus yp of 0, y prime of 0 minus yp prime of 0. Okay, so what I do is I'm going to say this is my A vector. This is the C vector I'm solving for. And this is my B vector. So let's look at what I put in here. So I wrote in two variables, y underscore 0 and y underscore prime underscore 0. These are my two actual initial conditions. So I'm going to use those to define my B vector. But I'm also going to need to know what y particular of 0 is. So what I did, notice here, here's y particular, right? Y particular, we determined that was b cosine omega t plus phi, right? So what I did was I have variables for b, omega, and phi written into my code elsewhere. Now, because phi in my code, as it always is in terms of degrees, I have phi times pi over 180 to get it into radians, okay? Because Matlab always assumes radians for these trig functions. And I plug in t equal to 0, okay? Now, similarly, I do the same thing here. I take the initial condition for the derivative, and then I take and I plug in here for myself the actual expression for the derivative. Now notice there's no minus sign here, right? Even though there's a minus sign here. And the reason for that, of course, was there was a minus sign when I took the derivative of cosine, okay? So that's why that plus sign is there. So if you look at this, you should see that this is the expression for the derivative evaluated at t equal to 0. Now, notice y of 0 minus yp of 0. Then I put a semicolon to go to a new line in this b vector. So y underscore prime underscore 0 plus the derivative of the particular solution. Key thing here is I separate those two things by a semicolon to get two different rows. Now the matrix here, A, is 1, 1. So 1 and 1 are on the same row. And then S of 1, S of 2. So in this case, I have a vector somewhere that says S is equal to, and if I look carefully, I believe it's minus 3 minus 1. Minus 3 minus 1. So I wrote S of 1, that'll be minus 3. S of 2, that's minus 1. And then I use that expression C equals the inverse of A times B to get my two coefficients. All right, so by the time this is done, I have that YC of T is equal to 0.6687 e to the negative 3t, right? Because S1 was minus 3. And that's then minus 0.6540 e to the negative t for t greater than or equal to 0. That is now my final transient response. So I got to put all those together to make the final plot. Now in this case, I gave you the t vector. I said for this t vector, what I want to do is I want to plot yp, yc, and then the total solution. Now this you're going to want later. All right. In the homework, I use this exact same form to plot all three of those at once. Now the thing that you should recognize here is which ones are which. Well, the particular solution is this guy here, right? He's always a cosine. The thing that's just the pure exponential, the red there, is y sub c. And then the combination of the two is this yellowy orange waveform that kind of, it's where I basically see the particular solution following the transient response. In other words, the particular solution is always there, but it has this transient response added on top of it that eventually is going to go away. So by the time I get to steady state, the transient response has gotten to 0, and the particular solution and the total solution look the same. And that's always the case. By the time you get to steady state, the particular solution and the total solution should look the same. Now, so basically what that gives me in summary is a set of steps like I have here, right? So I get the transient response, and when I'm dealing with second order, that means I'm basically going to get to that characteristic equation. Then I'm going to get the particular solution by guessing a solution that looks like the input. So if I have a step, I guess a step. If I have a cosine, I guess a cosine, and I go through those steps to convert it into the dynamic phasor and then convert it back out to a cosine. Then my last step is I get the unknowns in the total solution with the initial conditions. So I found a couple of things. If you look carefully in this, what I do is I find the total solution, right? Total solution is going to look like this. I write the derivative of that. I put the initial conditions together, and then I write a system of equations in matrix form to solve for C1 and C2. Those are the steps that we follow. They're the same no matter what. I should be careful about that. Not necessarily no matter what. The one possibility, if you follow this process, this works just fine when I'm looking at overdamped, underdamped, and undamped. If I got into the critically damped case, remember I would have C2 times T e to the S2T. That case is a little bit different, but like I said, I very rarely talk about critically damped because it's really not all that common in practice. All right. So that example should help you with some of the stuff on the homework.